Hello everybody, and welcome to today's CPD webinar in our series covering flood risk assessments. My name is Peter Coombs, and today's webinar is focused on modelling a blocked culvert. I'm pleased to introduce you to my colleague who will be joining us to demonstrate how we can fully utilise the benefits of using XPSWMM, and that's Ludmila Fadeva. For those that are first-timers on the webinar, welcome. And to introduce you to Ludmila, Ludmila is a drainage engineer with 9 years of both design and modelling experience in the UK as well as overseas. And when I say overseas, I mean specifically in the Middle East region. Now, due to the numbers attending the webinar, we have had to mute everybody, but please feel free to send us any questions in the GoToMeeting message box that will be shown on your screen when you've logged in. So I'll endeavour to answer your questions as we go through the presentation. So after this brief introduction that I'll run through now, I'll hand over to Ludmila, who will demonstrate how to use XPSWMM software live to set up a range of different scenarios, including how to model a blocked culvert. In terms of the guidance, one of the documents I'd like to refer you to is one of the later guidance documents that have come out recently, the Channel Management Handbook. It's a really useful guide, and it was published in March of 2015, so March of this year. The reason I like it is because it contains a lot of useful decision-making matrices, as well as a number of case studies, which I always find really invaluable. And as you can see here, culverts are often positioned within a natural channel network. And we can see that typical channel management issues that may also affect the culverts are sedimentation, vegetation, and debris. If we look at sedimentation, it's a natural process and it's essential to the functioning of the local ecology, the geomorphology and hydrology. However, sometimes we need to intervene because we have situations where maybe the capacity of the channel needs to be restored or it has to be improved, or we need to help the self-cleansing velocities to resolve some localized flood risk management or maybe some land drainage issues. And vegetation is a natural part of the channel ecosystem. However, excess vegetation and seasonal variations can create problems within culverts, causing them to block, or even the channel roughness can be quite radically affected, and that can increase and reduce the conveyance capability, as well as increasing the water levels within the channels as a consequence of those increased roughnesses. And debris comes in many forms. Some of it's natural and some of it is man-made. Now, this is a kind of good, bad example. It's an example of a poorly designed man-made constriction. Now, this safety grid has subsequently been replaced, and effectively it's a box coming off of the wall. So we can show you some photographs of the finished job, really. But this is not the way to design a safety grid fixing. And as you can see, that the pipe here, or the culvert, is virtually full of trash and rubbish. So let me set up the scene in terms of the live demonstration that Ludmila will now run through. We're going to start off with a base scenario, and that's a 1D model of just a natural watercourse. And when Ludmila shows you the dynamic long section views, they will appear sort of brown in color. So if you look at the top section here, the long section, showing the base scenario, when it's all brown, that's effectively saying that's the channel at the surface. The second scenario that Ludmila will run through is how to design a culvert to convey the flow that's occurring there right now satisfactorily. And that's the second shot down. So if you look at the culvert scenario, you can see that there's a sort of white zone here. This is telling me that there is depth of cover above the top of the culvert. So you'll see the sort of blue is the depth of the water within the natural watercourse, then flowing through a culvert and then through a watercourse on the downstream side to the right-hand side. And then in the third scenario, the culvert will be partially blocked. So what Ludmila is going to do is she's going to create some sedimentation or debris in a certain depth of the culvert. So if you look at the blocked culvert scenario at the bottom of the screen here, you'll see there's a black zone. So that black is showing you the area of the culvert that's effectively been blocked off. And then we're going to see the outcome. So finally, what we'll do is look at the consequences of the blockage. Now, that blockage could be caused by the sedimentation, the debris that I've covered earlier, or maybe a lack of maintenance. So you may want to put in scenarios to say, if we do not regularly maintain the culvert, It could half block or three-quarter block or totally block, for example. So what we'll do, we'll look at the effects by integrating the 1D channel with the 2D. So we'll see those effects by illustrating the subsequent overland flood flow routes as a sort of fourth illustration. But without further ado, I think that's enough of an introduction for me. So I'd like to hand you over now to Ludmilla, who will run through with a live demonstration for you. Ludmilla?
Thank you, Peter. So today we will start with a base scenario. At the moment we have only one scenario in the software, which is base scenario. And this is a scenario of a natural watercourse. So this is a 1D model of a watercourse. If we look through a long section, this is our long section of a watercourse. There are some sections assigned to each link, and there is an inflow assigned at the top node of a watercourse. But at the moment, when we run the model, we can see that there is no flood indicators, and our 1D model works perfectly fine. In 1D, the indication of flooding is only flagged at the node location. So if we go back to the plan view, so you understand better, if we click on any link and view the data behind the link, so we will have a section, a natural section assigned to every link. And as well, we do have, in the first node, we have some user inflow assigned, a hydrograph. And we do have in runoff mode a catchment of 50 hectares assigned with a rainfall parameters as well. I'm not going to stop how to set up a river and how to add inflows, because we did cover it in webinar number 1 and number 2 of our series. But what I will do now, I will show you how to replace a natural section with a man-made section, a culvert. And then we will run the model live, and we will see what happens when a culvert is there, and we will check if the proposed size of the culvert is good enough to convey the water. If it is not, we will ask the software to resize the culvert based on our requirements, and then we will make this culvert blocked and see the consequences. So I will zoom in at this location where I'm going to introduce the culvert. So at a link 6, at the moment we have natural sections. So again, if we go inside, there is a natural section with some levels assigned. First of all, what I will do, I will create a new scenario. So I will say new, and I will call it culvert. So I will do my changes in the second scenario, because I would like later to compare the results, such as water levels and flows, flooding values, etc., with my base scenario. So within the culvert scenario, I will change from natural section to a circular section. And I will put a diameter of 1 meter. And I will run the model. The software will ask me if I would like to rewrite the results. I would say yes. And the model will live run now. So what we can see in here, the bottom part of the window has percentage. So it shows how many percent has been completed of a first scenario. And then the top one shows both scenarios in total. So now we are running scenario 2 out of 2. And you can see the 1D engine works quite fast. And in a second, we will have the results. So we will be able to see what happens with our culvert and how does it affect the water levels. So if I zoom out and again select the whole watercourse, and I click on dynamic long section, what we can see in here, if I play the model, we can see a slightly different story than it was before. You can see that we do have flooding, and our hydraulic grade line at some sections goes above the ground level. And if I zoom in at the culvert location, this is what we can see. So basically the culvert works as a bottleneck, and obviously it is not enough size to convey the flow which we require to convey. At this point, what I would like to do, I would like to go back to my link 6 and ask the software to resize the culvert to convey the flow. For that, we have conduit factors window available. So in here, there is a section which is called design for. So I would like to design it for 100% of full depth with a minimum cover of 2 meters. and maximum number of barrels if we need any 3. So I don't want to have more than 3 barrels in parallel, and I don't want to have less cover than 2 meters on top of my culvert. I will rerun the model. So what will happen now? The model will again run both scenarios. So the first scenario and the second scenario. But the first scenario, we didn't do any changes. But the second scenario, we did ask to design the culvert. So what we will see, these blue rectangles, which in the first scenario were going like 1 by 1, just completing the percentage. In the second scenario, they will appear and disappear. This is because the software is doing iteration. So it is trying different pipe sizes, different barrel numbers, etc. to fit your requirement. So once the software has completed the iteration process, it will just complete the simulation. So at this point, it has upsized my culvert and it just completes the simulation for all other sections of my model. So we will wait for results for a minute and let's check what happened. Again, if I zoom out, select downstream objects and go back to a dynamic long section, we see a better picture. So this is a scenario culvert. Remember, we have a culvert in here. We have no flooding anymore, so we are not experiencing any flooding. And if I zoom in at the culvert location, this is the size which was proposed by the XPSWM. So obviously what I want to do now is I would like to check what size did XPSWM upsize my culvert for, to make sure I'm happy with it. By the way, you do set up your own pipe lists. So the diameters which XPSWM is using, set it up by user. So it's not just some random numbers. You can set up your own diameters which you prefer or which are in use in your country and work with them. So if I go back to my section, you can see it's upsized it to 2 meter, 0.35 centimeter internal diameter. And if I go back to conduit factors, I can see number of barrels is 1. So basically we are fine with one big pipe of 2.35 meter. It sounds very good, but now what I would like to do is I would like to block it. So I will create another scenario and I will call it blockage. But what I will do at this, okay, so I will say okay, and I will change my scenario for blockage. I will go back inside the link. And within the conduit factors, there is a special parameter which is called sediment depth. I would like to introduce a sediment depth of 1.5 meter. I would say okay to that and okay to that. But before running the model, what I would like to do, I don't want to run 2 previous scenarios because we basically did run them. We did get the results we wanted. So I'm quite happy. So I want to save my engineering time and just run the last scenario. So I will untick in Scenario Manager the previous 2 scenarios and we'll run only the last blockage scenario. It will save us some time. So because obviously if you have a watercourse with many culverts on it and you are doing iterations, you may have 10, 20 scenarios and you don't want to run the scenarios which you have already solved the problem. So you can then choose which scenarios you would like to run. Okay, the results are ready. All I do now is I select the downstream objects and I look at dynamic long section again. Remember, the scenario is blockage. We can see the flooding again. And it's not as bad as it was with 1 diameter of a culvert, but we still are experiencing some upstream flooding. So, and if I zoom in into my culvert location, you can actually see that there is a blockage within the pipe. So this is a very quick way how to analyze 1D elements of your natural watercourse. Obviously, apart from long sections, you can review your results in tables, where you can see such parameters as duration of flooding, or you can see some volumetric, velocity, flow parameters. The tables are manually edited, so you can add different variables to them and check your results. Apart from having results for one scenario, you can select all scenarios and compare results in between all scenarios. But at this point of time, what we would be possibly interested to see is what is the water spread of this blockage scenario. And for that, I have set it up a separate model where I do have a connection of my 1D model to 2D. In this scenario, I do have a grid extent assigned to my area of interest with a grid size of 10 by 10 meters. And I do have some interface connection lines which will connect my 1D watercourse to a 2D grid. As well, I have some extra layers like inactive layers where I do make my river inactive. So my watercourse is inactive. This section is not participating in 2D analysis because it's covered by 1D. So what I would like to see now is my maximum water depth. If I take maximum water depth, what we can see is some flooding upstream. So our culvert is located at this location, where is the link 6. So upstream, we have some water spread and flooding, which is absolutely fine because we know that in a blocked culvert scenario, we did have flooding. So our 1D model have indicated a flooding at certain nodes. But what we can see as well in here, there is some downstream flooding. And we do remember that in our 1D model, we didn't have any downstream flooding. So question is, why do we have a downstream flooding? So let me zoom this location in and try to explain you. This will help to understand what is the benefit of having a 1D, 2D model. So if we take a link, which is located in here, a river link, and we edit the data and we check the cross section, we can see that our left bank is 67.2, left one is this one, and right one is 66.6, which is on this bottom side. So if we look at our 2D cells, which are in here, we can see that wherever the 2D level of our land adjacent to the riverbank is above or equal the top riverbank. So see 66.7, there is no flooding and no breaching. But as we go along, it's 66.3. So the 2D cell is below the level of the top bank of the river. So that's why it breaches out, because it matches it together. So this type of analysis cannot be done within 1D model, because in 1D model you connect nodes together, but in 1D, 2D model you connect as well the adjacent land to your 1D model. So basically, if you have any levels along the riverbank which are below your section, it will show flooding in there. That's it from my side for today.
Perfect. Just a quick question, Ludi.
Yeah.
That came in. If you go back to the model.
Yes, I am.
And the question is, what if it's not a culvert, but maybe a bridge? So there are some folks that haven't been on the previous webinars. So could you represent a bridge?
Yes, we can. So at this point of time, this link is just a single link. It can be either natural section or different shapes or a special shape or a user defined. But as well, you can convert this link into a bridge link. So when you convert it into a bridge link, you will have a slightly different view. So this will be your bridge link, and there is a shape. So obviously you can change the shape or use the shape which was generated by the software. And then you can specify either bridge, or you can have a culvert option in there as well. It looks pretty much and works like a bridge in Hackross. So if any of you are familiar with Hackross bridge, it is pretty much the same. But yes, there is an option to introduce a bridge instead of culvert and do exactly the same analysis and get the results.
Thank you. And another question from Mohammed was, he's been working with, you mentioned Hackross, he's actually been working with Hackross.
Okay.
So if you've, say, produced the channel in Hackross in the first instance, could we do something with that rather than having to remodel it all over again in XPSWM? And if you do that, does it bring in the subcatchments that are generating the flow as well?
We can import Hackross data, and in here we can import either the whole model from Hackross, which will take everything over, or some cross sections only. So basically, when you locate your G0X file from Hackross, You can then select which parts of the model you would like to import into SWM. And then you can reuse them within the SWM software.
Yeah, so it's not just the geometry, it brings in everything with the model as well, the subcatchments too.
I think so.
Yeah, great. And a follow-up question, which was looking at the 1D with the 2D link. Obviously, the grid square sizes then, when it comes to analyzing the overland flood routing with the 2D, the choice of grid square is important to get the accuracy of the breach, if you like, over the riverbank as you're showing there right now.
Yeah, so obviously the smaller your grid is, the more accurate analysis you will have. And if, say, this is 10 by 10 at the moment, right? So if we had 100 by 100, maybe it won't even show it.
Yeah.
Because the average level of the cell would be different. Because if we just zoom into any cell of the model, and if I move the mouse down here, there is a Z coordinate, right? And if I move, the Z changes. But what the software does, it calculates or interpolates the average elevation for this 10 by 10 cell. So say if it would be on a very steep slope, 10 by 10 would probably not represent the actual level at that location. So it all depends on topography.
Exactly.
And the size of the grid.
Everyone's been really impressed with the speed at which the analysis took place with the 1D. It was really quite quick. With the 1D, 2D, how long would it take for that kind of model to run the analysis typically?
Okay, so in this model, I did have 3 different scenarios, and grid size was 10 by 10, and we did have 20, let's say 7,000 cells. I think one scenario did run about 15 minutes, but obviously it depends on your time step as well. So the bigger your time step is, the faster it will run, the smaller it is, more time will be required, and as well on your grid cell size, because the calculations are done per grid cell. So software does calculate every grid cell separately. So the more grid cells are there, the more time it will take. It depends as well on your DTM. If your DTM is very dense, and you have a lot of points, it may take a bit more time.
There's a supplementary that's come in on that because some folks are working with mixed catchment, so they have some flooding in like an urbanized area, but they also would like to incorporate some of the rural runoff aspects as well, like you're showing there. So could you have, like different grid cell sizes, if you like, so more dense where the critical flooding is in the urban part, but then larger grid squares where it's not quite so important, if you know what I mean, in the rural aspect.
You can create more grid extend layers. So at the moment we have 1 layer, but we can create more layers, and we can then draw. Let me just untick this and this. Okay, so we can draw multiple grid extends and give them multiple sizes. So depending on what area needs what type of analysis. So we can say in here that this, we want it to be 100, say 100 by 100 maybe. If I just untick the surface, 1, this should be 1 and 100. Okay, so this is 100 by 100, and this one can be, let's say 20 by 20. And when we run the analysis, we can obviously have different type of results based on the land use and the type of land we're running it for.
Perfect. Okay, well, thank you, Ludmila, and thank you all for your questions and for your participation. I really hope the presentation helped to show how quickly and how easily we can set up the 1D channel models with a range of those hydraulic sections, such as culverts, and then run scenarios to assess their various performance characteristics. And also how important it is to combine the 1D with the 2D to obtain the best possible assessment and the best outputs to highlight the consequences of poorly maintained or maybe blocked critical structures that you find in your networks. So I'd just like to go on to the next slide and show folks what we're going to be doing over the next month or so. So just to highlight what's happening, well, next week we've got some micro drainage training here. that's happening in Newbury. And then at the end of the month, we have 3 days of XPSWM training for those that would like to attend. And then in October, we're off to Portland, Oregon, so the home of SUDS in many people's eyes. So Ludi and I will be out of action for the better part of October. We're traveling and then training again with microdrainage training between the 19th and 22nd of October. And I've got a trip penciled in for the end of October myself to the Middle East. So at this one in time, it looks like I'll be in Al-Kabar and in Doha. So around about the last week in October, maybe the first week in November as well. And we're also presenting a joint case study at the NC Flood Management Summit. Now, this is happening in October. We need to confirm the date, but we'll send that out in the newsletter to you. Essentially, Ludi will be at the summit, and there will be a case study using XPSWM by a lead local flood authority. So that's the plan of action there. And we'll give you the date after the webinar. The next webinar, because of the actions during October, will be in November. So we're looking at Wednesday, the 11th of November. We will be the same time in the UK, midday, but by which time we'd have gone back to Greenwich Mean Time. So the clocks are going to go back an hour. So for our friends that are visiting from overseas, there's going to be an extra hour's time difference, but we'll notify you of that and send out necessary registration forms by ECAST, etc. Just to mention the CPD certificates, we're setting up a new system as we speak. So what we have been doing is sending out and emailing PDFs of CPD certificates for those that have attended. What we're doing is we're setting up an automated process now. So first iteration is this webinar. After the webinar, we'll be sending out an email to you, and that will have a code and a link. It'll take you off to a survey, which you don't have to participate in, but we really appreciate it if you did, because we're going to ask you for content for future webinars, etc. It'll be very brief, but if you don't choose to do it, that's fine. You can skip through and then get to obtain your CPD certificate automatically. So just to mention to your colleagues, I know a lot of people sit around in groups, etc., over lunchtime, and I really appreciate that. But you'll have to just make sure that those that want a CPD certificate in future, if you can make sure that they register, even though if you sit in the group, then you can obtain that CPD certificate more quickly and easily straight after the webinar. That's the plan of action. Meanwhile, I'd like to thank you all for your participation once more and your attention. We really appreciate it. Thanks for the questions and thanks for the feedback. And we wish you all well until November. Meanwhile, take care.
Thank you, everyone. And I just wanted to mention that the questions which came after, we will reply them individually via email to the people who asked them. And as well, at the end of the series, we usually produce a frequently asked question list where these questions will be included. Thank you. Have a good day.
Thank you. Bye-bye.